We will now introduce one of the first machines that students study in this area, which is that of deterministic finite state automata. You can see everyday devices having a transition diagram, such as a vending machine, where it starts from an initial state. And say you put $1, let's say it goes into a cheapo state, versus when you put $2, then it goes into a loaded state, as if you are loaded. And then you can press a button, say M and M, and it goes into a fickle state because it doesn't cost that much. And it dispenses the coin back, the change, and then comes back. So these machines are widely used, but what we're going to study is the formal properties of such machines. And mathematically, there are several interesting properties of these machines. What these diagrams below show is what happens if you add one stack to a deterministic finite state automaton. That will be studied later in the form of push-down automata. And what happens if you add two stacks to such a deterministic machine? Then it becomes a Turing machine. So it's an interesting cartoon that introduces the series of topics that are going to come your way. So now let us dive into the basic callouts in the book. So let us look at the first sidebar, which should take us to an interesting machine to animate. Okay, let us try this one. And so the student, while reading this, can go into this module and try to exercise the functionality. Okay, so what we see here is a series of definitions that pertain to the basic properties and operations on DFA. I'm hoping that we'll get through it and then get to various other constructions in this module. So now what we see is the first machine that is presented as a tuple Q sigma delta Q naught F, which corresponds to a certain diagram in the book. And this is how the machine is depicted. We can try to decode what the language of this machine is. One can observe that this machine accepts anything that ends in a 1. Let us put fuse edges also and see how the diagram changes. So with fuse edges, it's a bit more clear, so that the machine accepts anything that ends in 1. And so long as there is a length count of odd number of moves, that's also respected. Okay, so odd and ending in 1 seems to be the summary of this machine. So this can be depicted using, of course, this animation panel can be loaded with this machine's description. So if you would like to try this machine's description, let us, but this is the state structure directly encoded. So let us come to this one where the animate will show us what this machine is animating. It's a different machine. So let us take this machine and put it to the animation panel above. So let us say I copy this one and I come here and wipe this out and put this other panel here. So I remove this string and this one. So this animation panel has been designed without the string markers and things like that. So if I now put animate, okay, so there is a syntax error on line 3. So I think this is also not needed because I'm already in the DFA panel. So I could eliminate this one or put a comment here. So put a comment here. So the markdown notation that you do submit to .object, you need all this. So now the machine has been drawn up. And now you can animate the machine. So 0, 1, 0, 1 doesn't get accepted. Maybe 0, 1, 1 gets accepted. Let us see. So at this point, we can animate and run the input and let us see what it does. So after 2 and 3 transitions and ending in 1, the machine has accepted. So you can actually see that the machine is indeed living up to its specification of ending in 1 and odd length. So like that, you can actually try to understand the machine either through explicit acceptance tests. And this machine probably has not been defined. So we need to define this machine, which was here, I guess, DFA 1. And MD 34, figure 34 MD. So figure 34 MD has to be run again, which I didn't execute. So when I run this one, accepts DFA, figure 34 MD is true for this string also. Okay, so now we have already shown the ability to run nth numeric before, so we can run it again. So when you run the nth numeric function, it actually gives you the numeric order. And then one can run the 34 MD acceptance like was already illustrated. So this part has already been covered in a previous module, but you can actually understand several other things you can do with a DFA. So suppose you want students to submit a PDF of your finished machine. That can be done. So let us execute cell by cell by doing a shift enter, shift enter. So these cells have been evaluated. And at this point, what you have is you can do a render. When you do a render command like that, it actually generates the machine. And one can then get the PDF of the machine from the Colab run session. So if you go here to the Colab run session and look at the files, there should be the dev02.pdf sitting here. So that's how the students can access, download and access that PDF that you generate. So now you can poke a DFA and extend its alphabet, totalize a DFA. So you could actually try these. Totalize is a way to add the missing transitions to a machine. So anything that is not specified will be sent to a black hole state, like here. So we can actually now look at another machine and you can puzzle what this machine does. It seems to respond to an initial 0, or even otherwise it accepts. After a 0 or a 1, it accepts. But then it has to see an equal number of zeros and 1 followed by 0. So try to decipher it. Perhaps this is beginning and ending in something, or equal number of changes of 0 to 1 or 1 to 0, things like that. So you can actually also read machines from a file. If these files are present, it will be read. And second last is an interesting machine where the second last symbol ought to be a 1, and you can run that. And now you can study De Morgan's law. De Morgan's law for machines is one where you have to have the ability to do unions and complements of machines. And we can actually run the union of two machines and try to draw this machine. So this is DFA odd ones and ends in 0, 1. Ends in 0, 1 is this machine, which we can understand to be ends in 0, 1, ends in 0, 1. And odd ones is already present here. So odd ones can be understood by running that. So what happens if you want a DFA that does union of odd ones and ends in 0, 1? The union algorithm will construct that for you. And then you can apply minimization, which is to simplify the DFA. So when you minimize this machine, you're able to get this machine, which has lesser states, but the same language. And once you have that, you can see whether these two machines are isomorphic, and they are not isomorphic. But then you can ask, are they language equivalent? And indeed, they are language equivalent. So after minimization, the machines are still language equivalent. And then you can try to find out which states have been eliminated during minimization by subtracting the states. And so now we can engage in a series of examples which goes through odd ones and ends in 0, 1. And then odd ones, the delta can be looked at. And the whole machine can be looked at. Let us see where this series goes. Minimization of that can be done. Now we can complement the machine. So let us say you are complementing DFA of odd ones and DFA of ends in 0, 1. And now let us do complement. Complemented machines are unioned. and complement it again. So complement the machines, union and complement again. What should that be? That should be the same as intersecting the machines. And that is then revealed by De Morgan's law, which then says, yes, indeed, De Morgan's law works because you can actually complement the machines, union and complement again, which is the same as the intersection of the machines. So hopefully these are all examples that will motivate you to now get into the algorithms pertaining to various machines and operations. And there is one last machine provided on minimization. And this will be illustrated later. And when you minimize the blimp machine, it becomes a simpler machine, things like that. So I think this is a good point at which we can now start looking into the DFA algorithms. So hopefully you liked what you saw, and we'll continue next time. Thank you, bye.